So, can you hear me?
Yeah.
Okay.
So the next talk is by Peter Zoller. No introduction needed.
Thank you, Mohammed. So I guess that this is sort of a part number 2 on the programmable quantum simulators. You heard Misha Lukin talk this morning about, for example, Rydberg tweezers and all of the corresponding possibilities. And in my talk here today, I'll mainly focus on actually ions. Let me emphasize that, of course, all of these efforts that we are doing should be seen as part of these NISC devices, but I emphasized that in AMO spelling, actually the noise is usually pretty small, so you write this thing with smaller letters. Okay, yesterday we saw IS actually with very big letters, so we are maybe not scaling up to these very large systems, so, but at least we have sort of, little noise. Okay. Let me sort of go back now, maybe, I don't know, 10 or 15 years. I know when I was actually giving talks, that it was very often of the type that one was kind of dividing the world. On one hand, we had quantum computing as digital quantum computing. Think about ions maybe in this context. And we had, for example, also quantum logic network models demonstrating quantum algorithms. And a completely separate world was actually quantum simulation in the sense of the analog quantum simulation. I've drawn here as one example atoms in an optical lattice. You have standing light waves, and at the end you put maybe called fermions or bosons inside, engineering interesting quantum many-body models. But the culture of these two communities was very different. Over here, this is sort of more like a condensed matter community interested in equilibrium and non-equilibrium physics, and they were not really concerned about, fidelities of quantum gates and all of these kind of things. This was really many-body quantum physics and sort of kind of an atomic physics version of what I would call condensed matter physics. These original quantum simulators that were built in this context, they led to very nice things. There's a very long list of stuff that was done in this context. But they were sort of, in my language, kind of very dumb simulators, because what you can do in this context is that you can, for example, build certain kind of Hamiltonians, say like Hubbard Hamiltonians, and you can do these things with a very high fidelity. And so if I sort of comment on this thing from the left and the right-hand side, I would say that this world over here was always, the ultimate challenges of the fully programmable and also universal, actually quantum computer. And in practice, you could do these things only for a very small number of qubits. And of course, eventually you run into the problem of having to do error correction. Whereas on the right-hand side, we have actually devices in the lab at the moment that are pretty scalable to a very large number of particles. Some of these optical lattice experiments are done with particles that go up to about maybe 10,000 or something like that. And on the other hand, of course, the Hamiltonians that we're able to do, again, think of the Hubbard models, would be actually very restricted. So in this sense, as I said before, these analog Hamiltonians are sort of very dumb. What they really know how to do is, really then very, very well, maybe this particular class of Hamiltonians that they would like to realize. So these Hamiltonians are restricted, but they come with a very, very high fidelity. But what we have seen over the last, 5 years or even 10 years is now that these dumb quantum simulators have become sort of more and more clever, to the extent that, for example, in this community, they built, for example, a quantum microscope. And the quantum gas microscope allows one to do, for example, a single-side readout, in a single shot, measuring all of these correlations. And of course, you could also go in and maybe address one of the single lattice sites that you have over here. And this has led to the notion that actually these quantum simulators have sort of learned more and more. They've become more and more what we do in the context over here, but maybe keeping the properties that we have here on the right-hand side. And this leads one to this notion of what we call now a programmable analog quantum simulator. The Rydberg arrays were actually talked about this morning. And Misha explained that if you look at this from the point of view of a normal analog simulator, you would write down, for example, a spin Hamiltonian like what we have over here. Or if you take, this is another example here, this would be actually trapped ion, 1D, and there would also be a 2D version of that. That you simply have, say, one ion string, you would write down then a model which would be a transverse Ising model. That has possibly, for example, here a long-range interaction that you can tune. But it could also be, in this case over here, also a transverse field. So they become programmable to the extent that you can add, for example, single-side addressing to the whole story. And of course, you would also have the single-side readout. And we believe that these kind of systems that we have here could be scaled up in an atomic context, definitely to 100, but maybe even a large number of atoms. And we also believe in the context of AMO that we have to do these things or can do these things without actually doing, for example, error correction. So in that sense, there's, I think, a very interesting window of opportunity in time, that will last, of course, only eventually a finite time, because the ultimate goal, of course, will be the universal quantum computing, where with these kind of systems we can, talk about quite a large number of qubits or atoms and so on, while at the same time, not having to do things like, for example, error correction. So I think that's very interesting, and my talk in the following will be along these lines. And the idea in these programmable simulators is that, essentially what we have here is this, that our quantum device can realize a certain amount of resources. It can do very well, say, this, for example, transverse Ising model that we have. And we also can do, for example, single qubit gates. But now what we can do is this, that we can sort of try to program these things, like we also program quantum computers when we talk about gates, by taking the individual resources, the Hamiltonian that I actually showed you earlier, and also then maybe the single qubit rotations, and chain them together and somehow build from these analog resource Hamiltonians that we have, then what looks like a digital quantum circuit up to a certain depth. So there's sort of a compromise in doing all of these things. So if you add more and more control to these systems, of course, what you get eventually is this, that you get the universal quantum computer out. And of course, both of these things that we have up here could be operated as a universal quantum computer, but there may be, a lot of point of somehow being in between of this whole story. So the idea is this, that we can actually program up to a certain point. They're not always universal. I mean, they can be made universal, but they're scalable, and there's sort of a trade-off between these things, and we would like to position ourselves sort of between the programmability, being scalable, but at the same time sacrificing a certain amount of, for example, universality in what we do in this context. So let me now show, I always like to show these slides over here, the situation that we have in Innsbruck. So, we are theorists, and of course we are very lucky in Innsbruck because of the close collaboration that we have with, for example, Rydberg's group and some of the other experimentalists. So we have our own quantum cloud, okay? And this is the Technic campus where we are. I mean, this is university labs. This is from the Academy of Sciences, where we, for example, sit. And if I take these two buildings, theorists like, for example, Christian and also Rick, and both are here in the audience, they are sort of, maybe playing on their classical computer, writing certain many-body codes, whatever fun they have in this context. But of course, we have down in the basement here from the groups of, for example, here Rainer Blatt, Rose, and also Ben Lennian. And over here, there would be a universal quantum computer in the group of Sena, Blatt, Mons, and Schindler. That there would be these devices, and we can actually access these devices, not only running, for example, the code that we are doing, for example, on our classical computers, but you can also access these devices over here, and not only sort of send some information there, but also collect data, and in the end, actually establish a quantum feedback loop. And the way how Rick and also Christian did these things is that they wrote codes that essentially has a flag in there, flag a quantum processing unit true, simply sends the same code that they had. Of course, there will be several layers of interfaces down to these quantum machines to run their certain codes. And sort of upfront, I also would like to say, and this is the reason why I'm writing here this lowercase n in this case, in the results that I will show you afterwards, this is an example of doing, for example, a variation quantum eigensolver. You get some simulated energy. This is theory. This is the corresponding experimental parts. And this is the fantastic agreement that we get between theory and the experiment, where actually 59% of the data are within the 2 sigmas. And so these theoretical predictions were made on models, how we understand these devices versus the experimental results. So this really shows that we can do that. And this was done for a device of the 20 qubits. You might ask yourself why 20 and not, say, 50. The reason is very simply based on the fact that the addressing unit for the 20 ions actually only works for these 20 ions, and it didn't work for the 50. Since a few weeks, they have now actually they have an addressing unit in place that talks to a much larger number of ions. So what I tell you in the following, there's the hope that we can do these things for a larger number of particles. These are the groups, this theory group, already mentioned here, Christian and also Rick who are here, and want to mention also, of course, Rainer Blatt, and actually Christine Meyer was the main part of this work that I will talk about here today. During the last year, I would say it was actually pretty productive. We essentially wrote two major papers that somehow belong, I guess, to the core of this conference here. And I will talk about both of them, but also add a little bit new stuff at the end that I find quite exciting, and there's maybe room also for a certain amount of collaboration here in this context. Variation quantum simulation of lattice models and self-verification. The self-verification part was the most important part over here, sort of recognizing that these programmable quantum simulators are sort of ideally matched to doing these quantum feedback loops that I mentioned earlier, and therefore doing actually variational hybrid classical quantum calculations on these things. And this was the work that just came out now a few weeks ago, and then here on, for example, also Renyi entropy from random measurements, where we ask question, can we measure entanglement entropies? And again, we are employing the fact that we can individually address and manipulate our atoms and our ions in this context over here. And we have certain software modules, sort of, quantum software modules that we can attach to our quantum simulation that will measure the things like, for example, trace of rho square, which is a purity, or which is the Renyi entropy corresponding to the entanglement of a certain part of our subsystem over here. And this leads to new ideas like the cross-platform verification that I would like to mention that here at the end. So let me start out by sort of reminding you what all of you know, but then at the end maybe putting also slightly different emphasis in this context. I said before that these hybrid classical quantum or variational algorithms on our programmable quantum simulators are sort of ideal, because what they do, I would like to phrase it in this way, is this, that given the possibly non-universal quantum resources, these are these resource Hamiltonian that are realized in our quantum hardware that may not be universal, but sort of these are really the things that the machine knows how to do. Within these given non-universal quantum resources, what is the best answer that we get for certain things? And this is then done in a quantum feedback loop, as all of you know quite well. And what's being done there is always to define a certain cost function, which is optimized on the classical machine. The important part, of course, is how many variation parameters you have. And this is the classical optimization part. If you do it wrong, then you might actually drown in variation parameters. And this was one of the main things that we had tried to actually somehow address in our context. And then there will be a certain cost function, and the cost function over here can be evaluated on the quantum machine, and it can be done in an efficient way. Let me emphasize that as a result of all of these things, what you get at the end is that you get the wave function sitting in quantum memory over here in your quantum processor, and this wave function might be sort of ready for some other task. So very often when we do, for example, quantum chemistry and so on, we might be interested in calculating the best ground state energy. But if you're interested, for example, in quantum sensing, and I will give you an example now, actually after that, we might be interested in getting the wave function out, because then the wave function becomes a resource, for what we would like to do then afterwards. So here's sort of two examples. We did this variational quantum simulation where we did the variational quantum eigensolver, but we did it now for lattice models. And the main point in doing these things for lattice models is that we would like to scale these things up, and in particular, include also symmetries in our variational wave functions. If you got a certain target Hamiltonian and you go to the experimentalist and ask them to realize these things directly, they would not be able to do that. But the idea is now, sort of with the given resources, to build up on our quantum device wave functions from these resources, up to a certain depth of the gate, including this variational parameter state over here. So this Hamiltonian is never realized. Working out the cost function by looking at these individual pieces in the Hamiltonians and then measuring these correlation functions, repeatedly. This takes a lot of time to run all these things, and we will afterwards see certain examples for that. So this is evaluated here in the quantum machine. Hamiltonian is never realized, but actually, in this context that I'm talking about here, the variational wave function at the end is not used. Of course, it could be used in a quantum chemistry context by calculating certain transition matrix elements or whatever these things are. I think an example that's from this point of view of being kind of useful, what we do in terms of generating a tangle state, is when we do what I would like to call variational quantum sensing. Think of a Ramsey interferometry. In the Ramsey interferometer, normally we run these things as actually independent particles here, and we measure then Ramsey fringes. That does our parameter estimation. And I think all of us know that if you use entangled states, say like, for example, spin squeezing as an example, we would actually benefit from the entanglement that we have over here, improving the output or the sensitivity of our quantum device. So in that sense, you might also think about using as a cost function the squeezing parameter and ask for the best spin squeezing, or in a more general context, and then optimizing the Fisher information. And we're doing these things at the moment. I will not have time to talk about it here. It works together with the people at Schiller. For example, Jun Ye, together with Adam Kaufman, they have demonstrated recently that if you build, for example, a Rydberg tweezer array, where the Rydberg allows you to do the entanglement in the way that we talked about it, but at the same time in strontium, you can run these things as an atomic clock. We can then use these resources from the programmable quantum simulator in order to run these things to get the optimal cost function here, which is the best squeezing for the quantum device. And again, this is sort of following the story that given the resources, you would like to get the best squeezing out, playing your variational games. Let me come back now to the problem that I mentioned before. Namely, we were doing essentially simulations, variational quantum simulation for a Lattice Schwinger model. And I think that you are probably not the audience who would like to know a lot about the Schwinger model per se. I just want to say that the Schwinger model is an example of one-dimensional quantum electrodynamics, where we have essentially one lattice over here, and of course you can have the vacuum, and all of you know that in the Schwinger model in quantum electrodynamics you can create electron-hole pairs here, and so you can formally write down models, and these models are the type that you got electrons and also anti-electrons sitting on this lattice. The ones sit on the even and also then the corresponding odd sides over here. And you can, of course, these are fermions. You can convert them by Jordan-Wigner transformation into spins. But of course, in quantum electrodynamics, we also have here the quantized electric field. But we are very lucky in one dimension, because in one dimension, what we can do is this, that we can eliminate this gauge field from our model. And at the end of the day, we can just get a model for fermions or for the spins alone. If you do all of these manipulations, you cannot do these things if you go to higher dimensions, then you wind up with a model, and due to the fact that you eliminated your gauge field, this becomes a very ugly model, and but it has certain symmetries that I will emphasize then afterwards. So then at that point, you're sort of left now that you have a certain model, for example, and you would like to calculate your ground state. The ground state is given by the Schwinger model and is written down here now in terms of Pauli matrices and so on. It's sort of simple to the extent that it only has actually two sigmas over here, but it's very complicated because all of these coefficients from this elimination of the gauge field, make this model very complicated, and it's kind of a little bit unhandy. If you think about implementing this thing directly, say on an ion trap simulator in this form, I guess it would be very hard. But this is now the target, which is never physically realized. But here on the right-hand side, you have your quantum resource, your physical device, and you take, in this case now, ions. And you have your resource Hamiltonians, the one from the transverse Ising model, but also then possibly the single particle rotations that you would like over here. And the idea is then, as we always do in this case, to generate now a family of variational wave functions where you have certain parameters, 1 up to a certain number n, and n can be, 15, 16 at the end. And you do these things down to the depth of your circuit. So including the depth of the circuit, you might get more and more entanglement, you might get more and more accurate, but at the end of the day, of course, you also have possibly more variational parameters. So saving in terms of variational parameters in this context is, I guess, quite essential. And how do we teach now the quantum device over here, this target Hamiltonian? The answer is, of course, it knows it via the classical computer, which via the quantum feedback loop is actually steering our quantum device to do then the corresponding optimization, where these expectation values, which are correlation functions of all of these sigma Pauli matrices that they have over here, will actually be measured on the quantum device. So the essential key why what we did was actually successful is very much related to observing that we could build what we call symmetry-protecting circuits. And I mentioned before that we have building blocks over here that build up our variational wave function from, for example, initially a product state. This would be an L state, up, down, and here. Then you apply these kind of Hamiltonians, but you would like, of course, in doing all of that, to make a symmetry-protecting circuit, and this can be done on the hardware and the software level, and let me sort of explain what it means without entering the detail. If you go to the Schwinger model back, the Schwinger model was a model for spins at the end, and it had certain symmetries. that came, of course, from the original model, like the total magnetization in the spin language would be constant. But we were very lucky in this case, lucky or clever, I guess more lucky than clever, that our quantum hardware, which is Hamiltonian, if you operate, for example, the transverse Ising model in a regime where the magnetic field, this effective magnetic field is very large, becomes like a flip-flop Hamiltonian, conserving this magnetization here. So in this sense, the circuits that you build up over here right away preserve symmetries that you would expect from the exact wave function that you have in this context. There were also other symmetries that are maybe a little bit less obvious. There would be a charge parity symmetry. And charge parity symmetry essentially comes down that when you write, for example, here certain variational, you would write down certain variational parameters here, for example, for the single qubit gates, that due to the parity transformation, there would be a relation between these gates and the corresponding variational parameters, that the one on the right-hand side would be just minus the one that you had on your left-hand side. And of course, in doing a lattice model, and this is also a key part, you always got a certain amount of bulk. So you would expect that the ground states, but also other states, when you do dynamics, that you would expect that there should be approximate translation invariance, and you can try to build this thing into your wave function ansatz in order to get them to account for these symmetries. And this, of course, at the end has the advantage of reducing the number of variational parameters here, in this case, in a very significant way. But at the end, we still did, as I said before, 15, 16. This was sort of the order of magnitude that one was able to do in this context. So let me go right away to the results. And I have to say that these things were really the result of a collaboration where on the theory side, Christian and Rick were the ones that were writing all of the software underlying these things and really understanding the physics and guiding the experiment. But it was also an amazing experience on the experimental side of being able to collaborate with the experimentalists here and to see that their machine really performed well. And there was sort of a long discussion of mutual understanding where one had to sort of lock in the right place. But I think at the end it happened in a way that I found very beautiful and very exciting. This is an overlap and kind of an overview that I want to show you. I want to discuss first optimization trajectory, the experimental results, talk about wave function fidelity, and Rick van Bijnen was the one who wrote the optimization algorithm for the noisy energy landscape. This was really a key to the whole problem. I will not really have time to talk about these things here, so I just want to mention the main results which are actually behind this thing. So the optimization trajectory, this is now for 20 ions, 15 parameters, circuit depths of 6. So we had one layer of icing, then single particle rotations, and icing, and so on. And the idea was this, to restrict the number of cores to the quantum simulator to actually 10 to the 5. And in doing that, you would like to do a global parameter search where you have 15 parameters, and 15 parameters is actually quite a lot in this case. We'd like to do a global parameter search, but at the same time, you allow 10 to the 5 cores to the quantum simulator, meaning that the classical computer, in running the quantum device, has to use these resources that we have over here, these 10 to the 5, to use it one hand to optimize and explore the corresponding parameter landscape, but at the same time then also optimizing to get the shot noise down of all of these correlation functions that build up the corresponding expectation values. This is a typical energy one, trying to converge down here to the ground state. You can see the dashed lines here, the red one here and also down here. These are exact results here for 20 ions where you really diagonalize the Hamiltonian for the model. And you can see here this orange line, you can sort of converging down here. With this red line here indicating what the current estimate is. So this is really sort of converging down in energy then here. And this is taking a snapshot out here. These are, for example, theory versus the experimental parts over here. And you can see that actually the agreement between theory and experiment during this whole runs is actually quite amazing. You can see in what we do over here, there's sort of blue dots over here. There will be some orange ones. And this is related to the fact that the algorithm here identified two local minima and sort of was trying to decide between them. And you might also ask yourself, what's the point of the story that we got all of these data points up here? Again, this is sort of, you might call it an artifact of the global optimization, where you explore the complete energy landscape. Then you try to identify certain interesting regions of where this minimum could be. And then at the end, there's a part of actually the refinement where you really try to focus in and to try to compare the energies and get them here then very accurately. If you take your final result over here for the parameters, of course, we know now the parameters, these variational parameters. It is very easy in this context to restore then the corresponding wave function in quantum memory. And what we can do is this is sort of over here, calculate, and notice that this is a theory thing over here. We can calculate the exact ground state. We can take the experimental variational parameters, and we can actually compute the corresponding overlap over here. So this is exact theory, and this is sort of experiment in the sense that we take the experimental parameters to calculate that. And you can see that in this Hilbert space, modular symmetries, the final wave function fidelity was something like 0.85, which, for 20 qubits in this really huge dimensional Hilbert space is actually quite a lot. Of course, it depends on the corresponding parameters that we have in the model and how much entanglement we have, but these were sort of, parameters that were roughly sitting at the critical point or sort of close to a quantum phase transition that occurs. So in that sense, I think that these results are quite amazing, and you can see here these optimization algorithms sort of focusing in here in these two minima, and at the end some are deciding. I guess the most exciting part about this whole story was for us that for 8 ions and also 10 parameters, notice this is only a much smaller system now, we can of course do the same story of converting down, but what we can do here is this, that we can also measure the corresponding variance. So having minimized this energy that we have up here, we can also measure the error bar. Just take your Hamiltonian and square it, and if you got an exact eigenstate, then the energy eigenvalue minus the Hamiltonian squared will of course always be larger or equal to 0, and it's only equal to 0 for an eigenstate. So we can try to compute this thing again on the quantum device, now programming the h squared, which is now a lot more Pauli matrices, and compute then from this the algorithmic error, and we would like to compare this error that we get over here with the distance from the first excited state. The first excited state was also measured then variationally. This is the corresponding experimental result over here. This is the ground state, and then you can see here now how this error bar as a function of time that really goes down. And this is again the comparison between theory and the experiment where we try to simulate on our classical computers, these corresponding runs. I think that's the first time that quantum devices sort of not only give you an answer, the energy is this or that, but also gives you then the corresponding error bar. And of course, it would be very nice to do these things in a regime where we cannot do the corresponding classical calculations. But notice that measuring h squared can become very expensive. On the other hand, if you use symmetries like in lattice models where we have, for example, a translation and variance, this may actually become quite reasonable. Here's another example of a quantum phase transition. I don't want to elaborate on this and just say that when you change the mass in the Schwinger model from plus to minus, this is the vacuum out here. If you take the mass negative, then you will have many electron-positron pairs. And this is a phase transition over here. Again, you can see great agreement between the variational and the corresponding order parameter that you would compute on your classical computers. Most interesting is the power probably down here, where we measure, and I will now elaborate on this a little bit more, measure the Renyi entropies here across a quantum phase transition. And you can see how this Renyi entropy, which is the entanglement entropy by looking at 1/2 of the system over here, would be actually measured on the quantum device with some sort of quantum software, you might call it, in the way that I would like to explain now to you in the following. And you can see that if you don't put in enough depth of your circuit, you sort of wind down here, and these 2 points, you have to go to a circuit depth of 5 in order to get theory and experiment to agree with what we expect it to be. So you can see at this point sort of this emergence of, we are programming on one hand, a variational ground state here. We are calculating the variance, and then on top we can recreate the wave functions and then ask for entanglement entropy. So it becomes kind of a complete package that you can program on this device. And I find it quite amazing that some of these things can be done for 20, or in this case, this was done now here for 8 ions. Yeah. And all of the underlying theory does not assume that there's really decoherence. Of course, one could add here decoherence or some phase noise onto these things, but the circuit depth that we have here is actually so short that the decoherence in this case didn't really play much role. So in that sense, let me sort of now come and tell you, a shorter part of my talk now here about these Renyi entanglement entropy measurements, what we do there in this context, and then also say a few words about this cross-platform verification for quantum simulators, could also be quantum computers, where we're actually hoping that there might be some collaboration here with the ion group in the future. to perform some of these things where we compare, for example, quantum machine 1 and quantum machine 2, looking at cross fidelities by certain protocols that for us kind of an offspring of what we do up there. And we also have a collaboration here with our chairman. I hope they spice me now extra 5 minutes. Or, okay? No, okay. To measure topologic invariance for the symmetry-protected topological phases with random measurements. Yeah? So Alexei is not convinced, or? Okay, good. Okay, yeah. Let me just give you quickly the background and sort of at the end then convert to the recipe that you can program in these experiments. Suppose you would like to imagine that you got a many-body system, and I just for simplicity draw one line over here and subdivide it in A or B. This may be in a certain quantum state, say the ground state of your system that you prepared. If you split the system into two parts, you get the reduced density matrix, rho A, and if you square take the trace, this is the Renyi entropy, which is like the purity of the system. So the total system would be pure, but of course the subsystem would not be pure, reflecting the entanglement. The question is how to measure it. Well, it's not so easy because normally the kind of things we know how to measure would be linear in the density matrix, and so we have to square it over here. And one way, of course, of doing that would be tomography. But again, tomography, if you want to do it for a larger system, is very expensive. For some of the Hubbard models, we would not even know how to do these things. But we can, of course, improve the tomography, the efficiency very much if you know something about your system that you would like to measure. And these properties are used in, for example, MPS tomography and all of these kind of ideas that are efficient tomographies, but you have to know something about the system. Now, some time ago, we and also others wrote papers that if you have two copies of a quantum system, you, of course, have rho tensor rho. You make yourself two copies, but you can see rho tensor rho is not the same as the rho A squared. How do you do that? Well, you can convert one, which is rho A tensor rho A, to the other one by what we call a swap operator. And we came up, ideas how to implement all of these things. And of course, Markus Greiner did these very beautiful experiments where he demonstrated some of these things actually in the lab. And again, Adam Kaufman at BSc is the first author I mentioned before. So what we wanted to do is to do some of these things on trapped ions. And I cannot tell the ion trappers, take two copies of the system very close by and make a quantum link between them. So we are only a single system, and this is where the story begins. And we were very much inspired by some work that was done long time ago by Stephen van Enck and also Carlo Benaca. And the story sort of goes like this. Well, if you don't have a single system, make yourself a virtual copy, like in a sense of a replica trick. And how to get this thing over here? Well, the answer is from correlations between random measurements. So the signal sort of is in the noise. I don't have time to explain to you how all of these things work. And so let me sort of go directly to the recipe and tell you what comes out and what at the end can be implemented in an experiment and can be programmed. I'll show you some results along these lines. Here you have your quantum simulator. This is your trapped ions, and you have prepared a certain state, like, for example, you've done a quench dynamics, and you would like to observe this as a function of time. But instead of doing the usual kind of measurements, you perform now here random unitaries, and I emphasize that the protocol that we have over here is the one that we have individual rotations of your spins. So this is not a global circular unitary. This is not a unitary taken from the circular unitary ensemble. These are just local random spin rotations that you have over here. And then you measure in your standard basis, and as a result of all of that, you get a certain probability out, but these probabilities will depend, of course, on these unitaries that you had over here, but you measure these things in your standard basis. So the outcome, if you do this experiment very often, is this, that you go through the random unitaries, but at the same time, for given random unitaries, you have to do the measurement very often to nail down these probabilities and to reduce the corresponding shot noise. The statement is now that, in cross correlations between different outputs, and this is one bit string over here, this is another one over here, and taking the average, and average now means taking average over the unitaries that we have over here, we would then get, for example, there's a certain formula behind that, we would get here a random variable. This is a Hamming distance over here. This is these probabilities and the cross correlation between these probabilities. You generate a random variable, and if you average these things over many unitaries, you get the trace of rho A squared. The question is, of course, how does it scale with the system size? At the end, this will always be, this is a formalism that's completely agnostic to the underlying quantum state. So there will always be an exponential, but the statement is that the exponential is much more friendly than the one that you would have for doing, for example, tomography in this case here. And the experimentalists, of course, were only convinced once they did an experiment. It was going up to 20 qubits with 10 ions. One would measure, for example, quench dynamics. Here's the purity, where you plot now the purity first for the first system. This is just a single qubit. The second one over here, this is the second point, is now for 2 qubits, reduced density matrix, and sort of increase. Well, if you got the total system, we would expect that the last point that you have over here would still be 1. There's some measurement errors that you can see over here, so the total purity was only 0.76. But now if you do the quench dynamics, you can see how this purity changes. This is theory including some decoherence over here. And the Renyi entropies here, you can see very nicely that the total system is pure or almost pure, but this is the entanglement entropy that you get when you sort of partition the system over here. So this is sort of like a software module that you can kind of plug in. Okay, thank you, 2 minutes. That you can sort of plug in this case over here. And the nice thing is also that you get all of the entanglement of all your subpartitions out from this protocol. The latest incarnation now we've been thinking about this is that actually we can do the same kind of measurement protocol, and this would actually be a lot of fun by comparing 2 quantum machines. I mean, we think of one maybe being in Maryland for some reason, no ions, and then maybe one being in Innsbruck, and you would take your favorite quantum simulators or quantum computers, and then sort of run your quantum machine 1 and run your quantum machine 2, maybe taking the same Hamiltonian, or what we believe is the same Hamiltonian, producing a certain quantum state, and then compare via a classical link, and this is what these probabilities are, the corresponding quantum state in a way that's hopefully much better than doing a quantum state tomography. Of course, in doing that, we can also include the theory over here, so we can also make comparison with theory. And of course, I noticed in this context that there's been a lot of papers in the community out there in quantum information, like this one here on the fidelity estimation from a few Pauli measurements. We sort of are coming much more from the side. Let's compare 2 experiments with each other where we know nothing about the quantum state. What they do over here is like an important sampling, based on the knowledge that they know the theory state, which is assumed to be a pure state. So it's slightly different strategies, but I guess that they're sort of maybe converging from different sides to, at the end, to some related messages. So in this sense, we can compare quantum machine 1, 2, and here possibly theory to the extent that it is still available. So how do we do that? Well, if you got 2 quantum machines and wave functions, you would write down fidelities over here. But actually the one for the mixed state, like if I take a subsystem from here to over here, would be like the overlap that we have here. And then you have to normalize things in a certain way. And there's different ways of doing it. You can do it like a geometric mean, or you can do it like a max. There's these Chosa axioms, for these fidelities over here. And this max norm, which is the second one over here, taking the max of these purities. So the question is how to measure these things over here. And of course, this now just goes back to what we did before for the Renyi entropy, where we said we do a quantum simulation, produce a certain quantum state, and we perform our measurements over here. These are the random unitaries, read out probabilities, and get, for example, the purity out by a protocol that I showed you before. You might do the same thing over here for a second platform, again getting the purity out. But if you apply the same random unitaries here as well as here, and this could be really 2 distant labs that we have, you might get the overlap or the corresponding density matrix out in a way that's more efficient than the quantum state tomography by just taking probabilities from here and over here. Must be the same unitaries, but notice, of course, you do this, you're sort of sampling this distribution here, so there will be a different shot noise here and over here. This was different from the Renyi entropy that we had before. But of course, the unitary was sort of always, the reproducibility on the same quantum device. This is a classical link. In the absence of having a second experiment in Innsbruck where we could sort of compare these 2 with our quantum simulator, what we did now was that Andreas Elm and also Benoit Vermersch took experimental data that we have from the old Renyi and took classical simulations and computed the overlap. And for 10 ions, you can see how this comparison here looks. This was, for 500 unitaries, a number of measurements over here, and these were just taking old data that we sort of reinterpreted. The real thing that we would like to do is, of course, that we would like not to have one experiment and then compare it with theory. We would like to do these things with 2 experiments, done at distant locations, and then really compare if these machines produce the same state. We could sort of do a poor man's version of that by taking data from one day, taking data from the next day, and sort of cross-correlating, and then getting results. Actually, you can see there's 0.85, so this starts to look actually already pretty good. The question is, how does it scale with the system size? And I just want to, this is almost my last slide now, say that from small scale numerical calculations, we take product, random states, and also mixed state. We see that this thing scales with a friendly exponential, where this b of up here is of the order of something like, say, 0.5 or 0.6 or 0.7. And this is the scaling that we can do numerically up to 10 qubits, which is roughly the system sizes that are being done at the moment in the lab. But of course, if we can also take a larger system, and we're quite sure that these things can be done for qubit sizes. I mean, by the subsystem you look at is maybe something like 20. But of course, at the end, the total system size must always also be limited, because if you got too much entanglement in the system, your purities will become then actually very small, disappear in the denominators, and then you got the problem here with error bars. You can have a lot of fun by comparing, for example, time evolution of different Hamiltonians and looking at the overlap and all of these things. So there's a lot of quantities out there that can now be opened in this context, but we sort of, I guess, got the point here. So let me come to a conclusion. So I was talking about atomic NISC, and I said that we're writing this thing with smaller letters and all smaller fonts for the noise part of the story, because we are atomic physicists. I talked about programmable quantum simulators with atoms and ions, and which sort of interpolate between the scalable analog quantum simulators and the universal digital quantum computers, and there's somehow life in between. There's an interesting window of opportunity for the coming years in this context. These things are very much, married to the possibilities of hybrid classical quantum and variational algorithms. Let me point out that these analog simulators not only exist, of course, for spin models. You can also do fermions, and would find this very interesting to go with fermions to 2D and play a similar game. The main problem there is that these experiments right now are actually too slow. And then, sort of outcomes of these things are also this cross-platform verification that would open an interesting opportunity, and also a collaborative effort where we can compare different quantum machines, maybe even over the ocean, and then sort of have here a comparison not on the trivial level of quantum simulators, where we simply say, okay, you produce this phase diagram and the other one that, and then just put it on top of each other. But you look at really the underlying wave functions, so reduced density matrices of hopefully relatively large size. So with this, I'm at the end here, and I want to emphasize again that the key people in this work here that I presented were Christian and also Rick, who are here right now, and also Andreas Elbert and Benoit Vermersch for this part that is related to the random measurements. But all of these things, the great benefit that we have in Innsbruck is that we are allowed to collaborate with experimentalists in this context. And some of these protocols that were invented here, they were not written up as theory papers. You go directly to the experimentalists and say, can you do that? And this is much more fun than just writing a theory paper by yourself. So with this, let me thank you, and also thank for the invitation by the organizers here to this conference.
It's definitely worth waiting a few more minutes for lunch. So go ahead.
Hi, thanks for a good talk. I had a question about the second part. Where you use VQE to find the ground state of the lattice Schwinger model. I guess initially the energy decreases steeply, so most of the cost is going to go into the classical optimization. But towards the end, the energy changes slowly, it converges. So I think most of the time will go into measuring the small changes in energy.
Why does the curve not go to the theoretical value?
No, I'm saying that it's going to get more and more difficult to measure a small change in energy, and it's going to require more and more cost.
Okay, so you're essentially saying that when you look at this curve going down, we could have stopped much earlier and gone home, and we would have gotten the same result.
When you go to larger and larger.
You talk about larger system, or you talk about going to a circuit depth that should be more and more and more? I mean, the circuit depth is kept here constant, and then you're sort of improving, and of course you always at a certain value above, in agreement with what actually theory also finds in this case for this variational wave function. So in that sense, this is consistent. I guess what you're saying is this: we should also put in deeper circuits and see how they do. But at that point, of course, you're facing the challenge of having variational parameters that increase very much, and we are doing this global optimization, which is actually a very difficult one. So Rick could actually tell about these things much more. This is optimizing on the noisy energy landscape, and you have to make compromises between optimization and then sort of narrowing down the error bars for all of these quantities which you measure.
So I was wondering when you tried to, you're doing the optimization trajectory for the Schwinger ground state, and you kind of asymptoted at 85% state overlap fidelity. Could you have raised that fidelity by doing like a quantum subspace expansion or something like that? Or are you limited by the analog device you're simulating on or something?
So I'm not sure I understand the question. So we were calculating theoretically the ground state and the excited state, and then we had the experimental results, which was the ground state from variational, and the subspace expansion was used to, for example, calculate the first excited state. And maybe I should go back to this slide, which is somewhere that you can look at that. This thing here. Okay, so this was our trajectory going down. This is the exact ground state. This is the first excited state over here. And then there was another one where we showed. Okay.
Yes, it was on the next slide I was asking.
For example, this is the first excited state, which was done experimentally with the subspace expansion. And you can see that the exact theoretical result is over here, and the experimental result from this variational first excited state is actually the one which is up here.
Right. So on the next slide, when you get 85% fidelity, I think on the right. So why couldn't this quantum subspace expansion have gotten you to higher fidelity just for that state?
Well, the reason why I don't go to higher fidelities, of course, that this was a fixed circuit depth, and if you put in more and more entanglement into the system, of course, you would expect that you go to the exact ground state. Yeah.
In the second to last slide that you showed cross-platform fidelities, can you comment on how you get the error bars?
Which one you mean? In
the cross-platform fidelities.
The cross-platform fidelities, okay. Maybe a more efficient way of progressing here. So. I mean this one over here? Or
no, the one that was between 2 days.
This one here?
No, before this.
2 different days. Okay.
Yeah.
Okay, so this one over here. So the way how this was done is this, that you sort of simply subdivide your data into 2 groups, okay? And you think that you apply the same unitary to them. This is the requirement what must be done. What the experimentalists not always achieve. So actually one of the main complications at the moment in the experiment is that the experimentalists were pretty sure that the unitaries were very accurate on the level below 1%, but it turned out that the error bar of the single qubit gates, when the level of about 1%, it did not show up in the Renyi entropy measurements, because there this error sort of drops out, but it came up here. And for example, when we compare with the theory, this was only 75, and this explained actually this main difference why we don't go higher and why you got, for example, 85% over here. So the experiment compares with itself much more accurately. Is that there's an uncertainty you have to calibrate, for example, single qubit rotations on an absolute level. These error bars that you have over here were simply taken by sort of subdividing your data that you had into different groups and then calculating from this thing, then here the corresponding error bars. So as I said before, we are very hopeful that maybe, because there's a similar experiment here in Maryland, that maybe we can do something here together, where a quantum machine in Europe and the one here in the US would sort of produce a certain quantum state that we believe should be the same, and then we use a protocol like this in order to actually verify. This would be, I think, the first cross-platform, platform, both are ions, okay, verification, or at least in terms of geography and also in terms of time. I would also say that these kind of things of doing this experiment on day 1 and day 2 is kind of interesting from the perspective. I'm not saying that you can see probably the change of the fine structure constant in this context over here, but sort of also for experimentalists to finding out to what extent the apparatus is changing as a function of time, because you sort of compare with the data from yesterday, and you might see your improvements or not when you do these kind of things. So I think that there's an enormous number of possibilities, and of course very clearly this applies only to quantum processor in the NISC regime. This will not work for an infinite number of qubits, but it will work for for the small numbers, and this can go up to maybe 20 or so. This would work extremely well.
And the other two speakers.